All right, folks, we're going to take a look at section 5.4 today on the concept of comparison tests. And there are two types of comparison tests that we're going to be looking at. The one that they call the comparison test, sometimes called the direct comparison test, and then the second one, which is called the limit comparison test. But let's take a look at the comparison test first. What the comparison test says is the following. If there is a value of n such that the terms a sub n are less than or equal to b sub n, and they're all positive, when your n value is bigger than that value n, then the comparisons that can be made are the following. If b sub n converges, then the sum of a sub n converges. In other words, if you can find a series that's larger than another series, and that larger series converges, then the one that's less than it will also have to converge as well, which makes sense. Likewise, if this series a sub n diverges, then the series that's bigger than it, the b sub n, diverges. And those are the comparisons tests we can do. Okay, so here's the idea. Let's take a look at exercises 198 to start, where we're looking at the sum as n runs from 2 to infinity. And the reason we're starting at 2 is because we're going to have the natural log of n in this. So natural log of 1 would make no sense at being 0. Okay? And we want to try to do a comparison of this term to another term that we have a better understanding of the convergence for. So let's compare 1 over n ln of n squared to 1 over n squared. And the comparison we would make is that when n is large enough, meaning n is bigger than or equal to 3, this inequality will hold. Because the natural log of 3, natural log of 4, and so on will make this denominator larger than this denominator, and therefore this fraction smaller than this fraction. Okay. Now, making this comparison, what I realize about this is the following. 1 over n squared converges. Because after all, it's a p series. P is 2 is bigger than 1. Means convergence. And so what we have found is this series that we want to analyze is less than or equal to this series. And this one, which converges, implies this one also must converge. This series converges, and we're done with the problem. Okay. All right, let's take a look at 196. So going back to 196, we have the sum from 1 to infinity of 1 over 2 times n plus 1. And so let's think of a comparison that we can make here. 2 times n plus 1. I want to compare that to the following, 1 over 2 times n plus n. So what I did here was I made the denominator larger, didn't I? So if I make the denominator larger, I make this fraction smaller than this fraction. n plus n is 2n, times 2 is 4n. And so the series I'm comparing this to is the following. This is bigger than or equal to the series 1 over 4n. And that, of course, if you factor out the 1/4, is 1/4 times the sum of the harmonic series, which diverges. So what you did was you found that this series diverges, and this is smaller than the series we're analyzing, so our series must also diverge. Okay, so you get the idea of the comparison that we're doing. We're comparing our series to a simpler series, in this case up here, 1 over n squared, because we know the behavior of 1 over n squared. Here we're comparing it to 1 over n because we know the behavior of 1 over n, and we're using those results to inform us about the behavior of our series that we're interested in. Now the interesting thing is, in both of these cases, the series that we compared to are p-series. And this really gives us an understanding of why it is we wanted to learn about p-series. They form a family of series to which we can compare other series and learn about these other series that way. Okay? All right, let's take a look at another example. Let's take a look at number 200. 200 has factorials in it. So what do I want to compare this to? Well, this n factorial, of course, is n times n minus 1 times n minus 2 times n minus 3, and on and on and on and on. Okay? So how about I simply compare this to the first two terms, n times n minus 1. Okay? So I've made the denominator from here to here smaller, making the ratio bigger. This is bigger than this. Okay. Now, can I make this even smaller in the denominator? Smaller in the denominator, making the ratio bigger. Well, how could I make this smaller in the denominator? Well, what I could compare this to now, to see what the behavior of this series is, n minus 1. Oh, yeah, I can make this an n minus 1 here to make the denominator smaller and the ratio bigger. So I'll have to start it at 2 if I do that. Okay. And so what I have here is 1 over n minus 1 squared. And so what does this do? Well, if I bump up the index here, or bump down the index, that becomes that, which is a p-series that converges. And so what you did was you found this series converges, and it's bigger than this series here. So this converges. Okay. So you see, it's a little bit tricky. You have to do a little bit of thinking about how to do the bounding in an appropriate way, so that you can get a series that gives you a result that informs you about the behavior of the original series. It's a little bit of a challenge, okay? All right, so we'll look at one last problem here. 206, yeah. So we have the sum, n from 1 to infinity, of the 4th root of n divided by the cubed root of n to the 4th plus n squared. Okay? This is bigger than or equal to what? Replace the n squared with n to the fourth. So I made the denominator bigger, making this all smaller. Now this is n to the 1/4 in the top. This is n to the fourth plus n to the fourth, 2n to the fourth to the cubed root. That's 2 to the third times n to the 3/4. Take the 2 to the third outside in the denominator. N to the fourth over n to the 3/4 leaves n to the half. And that's a p series. P is a half. Diverges. This series diverges, and it's smaller than this, so this diverges. Okay. And I have always found this type of a comparison fairly tricky to do, because it does require you to think about inequalities instead of equations as you're working. And for some of us, that's a challenge. Apparently for me, it's always been a challenge to think that way compared to equations, which seem pretty straightforward. All right, now the second type of comparison we do is going to relieve us of having to work with these inequalities, and therefore it's a comparison that I find a lot more useful. It's called the limit comparison test. And what it says is the following. Let's let these terms a sub n and b sub n both be non-negative for n, all the index numbers bigger than or equal to 1. Then the following three things are true. If the limit as n goes to infinity of a sub n over b sub n equals a value that's not 0. Okay? If this ratio in limit equals a value that's not 0, in effect, what that's saying is a sub n terms look like L times b sub n terms eventually. And therefore, either both of these series converge, or they both diverge. Because after all, in their tails, in their infinite tails, one series is just L times the other series. A constant multiple times this, you factor out the L, they're the same. They both have to have the same behavior. Okay. The second thing is this. If this limit, same limit now, of a sub n over b sub n is equal to 0, then if the series up top converges, the series in the bottom converges, then the series up top must converge. In other words, if this converges and this goes to 0, then this one must be smaller than it, must also converge. Bn converges implies the series up top, An, converges. Okay. And third, if this limit as n goes to infinity, think about what's the other possibility. It's either a non-zero constant, it's 0, or it's infinity. Well, if it's infinity, then the series down here diverging means the series up here diverges. All right. Now, let me try to explain the benefit of this type of a test. Instead of us having to work inequalities like we have to do when we do this so-called direct or comparison test up here, I no longer have to worry about inequalities. The limit process is what I use. Okay? So, the limit comparison test is a test you want to use. Use limit comparison when there are terms you want to get rid of in both the numerator and the denominator of a sub n. So you're trying to analyze some series. And you're looking at the terms a sub n, and you say, you know what, I'd like to throw away some things from the top, and also throw away some things from the bottom of that expression for a sub n. Okay? Then, well, if I was trying to do a direct comparison, when I throw something from the top, the inequality goes one way. When I throw away something from the bottom, the inequality flips, goes the other way, and the idea of making this inequality type comparison just goes out the window. Okay? But with the limit comparison, I'm allowed to do that because the limit process throws those terms away for me. And so let's look at an example. Let's go back to problem number 204. We have the sum from 1 to infinity of n to the 1.2 minus 1 over n to the 2.3 plus 1. You think, okay, I'd like to get rid of this and this, but I get confused about the inequalities and I try to do the comparison. Or maybe this is a plus 1 here as well. We can modify the problem. Okay. The limit comparison would allow me to compare to the terms where I say I'd like to get rid of that and that. I'd like to compare to that. Okay. Well, do that comparison in limit and see what you get. It doesn't really matter whether these are pluses or minus, does it? Because in limit, those are going to go away. And so what you're going to be left with is just this part here. Plus ones, minus ones are not affected when n goes to infinity. They go away. And these are the same, so you get the limit to be 1. Which means the behavior of this is the same as the behavior of this. That was our conclusion from the limit comparison test, right? If the limit is equal to a constant that's not 0, then both of the series, the one you started with and the one you're comparing to, both have the same behavior. Okay, so now what does this series do? Well, if you subtract 1.2 from 2.3, 2.3 minus 1.2, you get 1.1. That's a p series. P is bigger than 1, so that converges. Since this converges, this one must also converge. And it doesn't matter if it's a plus 1, a minus 1, a plus 10, a minus 30, it doesn't matter. Those are going to go away in the limit process. Okay. All right. Now, that's the nature of the limit comparison test. That's what it's for. Okay. So let's take a look at exercise 208, where the author asks you specifically to use the limit comparison test. N to the 0.6 in the bottom, and it's all squared. Okay? And so what I want to compare this to is this. Let that limit of n become 1 instead, and that meaning this is 1 over n to the 1.2. Okay? So that's the series I'm comparing this to. And so I'm going to do this by the limit process. This is going to cancel with this when it's squared. Okay? Oh, I should compare this to 1.1. How about we do that? That way I don't get a complete cancellation. So let's see. I'll rewrite this, make it a little better. All right. Now let's see what we have here. The ln of n is getting squared. N to the 0.6 gets squared to n to the 1.2. 1 over n to the 1.1. This flips up, cancels, leaving an n to the 0.1 in the denominator. All right. Now, taking the limit, this goes to infinity, this goes to infinity. And that's the setup to use L'Hopital's rule. So applying L'Hopital's rule, I take the derivative of the top. There's the derivative of the top by the chain rule. And I take the derivative of the bottom. Taking 1 away gives me that. Okay. Now this 1 over n has to come down here. It's going to cancel with the n to the negative 0.9. And leave an n to the 0.1. 2 divided by 0.1 is 20. Ln of n to the 0.1. Now, this goes to infinity, this goes to infinity, so again, L'Hopital's rule gets applied. The natural log of n's derivative, 1 over n to the 0.1 is 0.1 n to the negative 0.9, and again, this comes down here and cancels. This goes up as a 10, bring the 10 out, 200, limit, n goes to infinity, 1 over n to the 0.1. As n goes to infinity, that goes to 0. So we've done the comparison, comparing to 1 over n to the 1.1, and the limit was 0. Now recall, if the limit is 0, if the bottom series converges, then the top series converges. Well, the bottom series was this. That's a p series. P is 1.1, which is bigger than 1, so it converges. If that bottom series converges, then the top one also converges. So we have convergence in this. Okay? All right. Now, if you look through the exercises where the author has asked you to use the limit comparison, what you're going to be finding is something I find a little bit disappointing. The exercises here are more about exercises in computing limits than they are in really utilizing the concept of the limit comparison test. The concept of the limit comparison test, again, is to be able to throw terms away that are inconsequential in limit and do a simple analysis. It seems to me, when I look at these exercises, that the author has taken great pains to make clever exercises about limits instead. So unfortunately, there's not much in the exercises here that is going to benefit you in understanding the limit comparison test. Okay, so that's just the way it is in this section. It's not a lot of good work to be done in the exercises, but maybe you can do just the first couple of the exercises and get something out of it. Okay? All right. So not all of these videos have to be extremely long. Not all of the sections require us to talk a lot about the techniques. This is a very short section for you to look at. It's going to be relatively inconsequential in the overall scheme of the chapter, so don't get too upset about not being able to work some of these exercises. As I said, they're more about computing limits than they are really using the limit comparison properly. All right, so as always, if you have questions or concerns, don't hesitate to contact me. I always look forward to hearing from you.